Okay, so this lecture is the second lecture looking at model building. What we're going to look at here is a larger model, a somewhat messier model, and we're going to talk about a little bit about some of the real world implications of building models. So for this lecture, take a look first at the file AMS 2940 model building 2 background. This is the description of the problem. And in fact, I would suggest that you stop here and go give this one a try. What we are going to focus on through this lecture is I'm going to present a possible solution to this, but I'm going to be talking a lot more about some of the implications, the assumptions that you have to make, simplifications, because you can't model everything in the real world perfectly. You have to make decisions, you have to sometimes make simplifications or assumptions, and an important part of dealing with real world problems is noting what those are and making sure that your results are still valid even through these assumptions. When you're given a problem, there's many different ways to form a problem. Okay, things normally aren't as clean cut as they are in a textbook, and we're going to see through some of that here. So again, take a look at the download first and give this problem a try on your own. And then I'll step through one potential approach to it. Okay, now the first step in solving one of these problems or in producing a solution to one of these problems is your variables. I can't emphasize enough how important it is to write down what your variables are in as much detail as you can. So for this problem, we're going to work with the following variables. And really what I'm trying to capture here are all the things that you either have control over or things that can change. So for instance, what do we have control over, or what are the things that can change? So it's the sale price of the crop, that's the PIs. The XI is the area of the crop in hectares, a production rate of the crop in kilograms per hectare, a fixed production cost for the crop, a water cost for irrigation, and an irrigation depth for the crop. So reading through the problem, I've tried to pull out all of the things that can change. And you'll see even one of these is a set number. We know exactly what that number is. But I'm going to give it a variable name anyways, because it is something that could change at some point, and we may be interested at some future point in saying, well, how does the solution change if that item changes? So when you're dealing with complex problems like this one, with a lot of different variables, it's actually very common to try to simplify it a little bit. So in real situations, there's usually too many things to model completely, or there's some unknowns in there, and you have to simplify the problem. But it's important that you note how you simplify the problem. Maybe there's a variable that you aren't going to take into account right now. Maybe there's some kind of connection that you're going to make a few assumptions over. These are perfectly legitimate things to do. They're perfectly legitimate steps in providing a solution, but it is important to note what these are. And quite often it is very common to do these problems in an iterative way. So you start with a simpler problem with a number of assumptions. Then after you find a solution to that, you'll take a look at those assumptions. You'll say, okay, in light of my problem, is this an important thing or is it not important? Is my problem going to be sensitive to this? In other words, if I make a small change for this input, will I get a significant change in my output? Or is it something that really doesn't matter in the long run anyways, and I can leave it out to simplify the problem? It's very common when you're dealing with these problems. But it's also very important to note what these are so that you record what they are, your audience, your client understands what simplifications have been made, and it's easier for you to go back later and readdress them in a further iteration of the problem. So for instance, for this one, we're going to make a simplification. We are going to say that for the varying yield of the crop based on irrigation depth, we're going to simplify it somewhat. We're not going to take that into account right now. Maybe we'll go back and look at it again later. But to make the problem just a little bit easier to try get our heads around it, we're going to simplify it first, but we note what the simplification is. So we're going to make the assumption that the minimum depth for each crop produces the yield given in the problem. So we don't have to deal with this right now. Maybe we'll deal with it later. Okay, so first we're going to look at the objective function. And the problem here is we're going to maximize profit, which is given by this formula, which is missing an equal sign there. So we know the value of CW, so we plug that in here in the second half of that formula. But this formula, once we put it all out, we simplify it using what we do know, we come up with a value for Z, which is our profit, which is what we're trying to maximize. Now note also here that I've added another assumption. If you look at the problem itself, that isn't in the problem. So the problem is giving you a set yield per year. But what we'll often do as well is add assumptions that kind of encompass the larger context of the problem. If you know about farming, you know that yield will vary from year to year sometimes, and that there's a lot that goes into it. So we're going to make a simplifying assumption for this problem that the yield per hectare is as given in the table and does not vary from year to year. Now this is another one that later on you could take a look at it and say, okay, what if my yield does vary? Does this affect my result? But again, the more assumptions and simplifications that you can write down, the more robust your solution will be. So now let's start looking at the constraints, and we'll step through a few of the constraints. First off, water supply. We have 10 different water supply numbers in here. So you take them, you add them all up, we get an overall number for the amount of water supply. Now this leads to a couple more assumptions. So again, the better you can list what your assumptions are, the better your solution to the problem is going to be. So a couple of things is that this uses overall water supply for the year, it doesn't break it down into monthly requirements, because as crops grow in different times of the year, there may be different requirements for water. We aren't breaking it down by month, but again, that's something that you could go and address later. A second is water availability. We have an overall number for the year. We're assuming that the water is available when needed. Maybe there are seasons where there's water shortages and water is not available as much during hot months as cooler months or through rainy seasons. That's a valid assumption, but we have to write it down as an assumption that this may not be reality, but we're going to make this assumption to simplify the problem a little bit for now. And again, we can take a look at it again later. Our next constraint is about the land supply. Again, looking at the problem, we have a number for the total land supply. But there is also an inherent assumption in here that it's assumed that each area of land grows only one crop per year. It doesn't say that in the problem anywheres. It doesn't specify whether or not it's possible to grow multiple crops. If you look at the crop schedule, it looks like there may be ways when you could grow different types of crops during different seasons, but we don't know that. So we're making the simplifying assumption again that each area of land will only grow one crop per year. And finally, the problem tells us some limitations on specific crops. Some crops it says we can only grow so much. Some crops it says we need to grow a certain amount. So we can write down those limitations as well as additional constraints. And finally, our non-negativity constraints. Now again, when you go through this, the assumptions are all important. The more you can kind of list what your assumptions are, the more robust and a better solution you will have for your problem. Okay, so now we're at the point where we have a fully formulated linear program. We have something that you can go and solve. But now let's take a look at the assumptions. So now we go back to it and we say, okay, well, what if the assumptions can we do it a little bit better? And for instance, one of the assumptions we made on an earlier sheet was that each piece of land only grows one crop per year. Well, what if it can grow more than one crop per year? Well, then we can start to refine our linear program. So to do that, we have to start looking monthly. So every month, there's certain crops that grow. We can add up the land used by each of those crops for that month, and it can't surpass our 17,750 hectares of land. But now we're looking by month, and this is saying we can grow multiple crops. So this is taking that assumption, refining it a little bit, and changing our program to deal with it a little bit more. Now there are other assumptions that are built into here. But again, if you can identify what those assumptions are, you're going to be doing you're going to be improving the solution of your problem, and you'll be getting a better solution each time you do this iteration. So we also had an assumption about water consumption or water supply. We said that water supply was consistent and you could always meet your water supply. Well, what if that's not true? Well, maybe we have to look month by month at what the water supply is. Again, taking that assumption we made, refining it, and doing it better. Now you could have assumptions in here that the daily consumption or daily supply is consistent through a month. But at least we've taken our assumption and we've made it a little bit better. Okay, so this lecture was just intended to give you an idea of some of the complexities of building models in the real world. And the whole idea that you normally can't try to model everything. You have to narrow it down to what you can model, note what the assumptions and simplifications are, and then take your solutions and go back and redo your problem with those new assumptions or by refining those assumptions. Try to improve it. Model building in the real world is an iterative process. You normally have to address and readdress, and as things change, you have to look at your problem again.